Today, we will simulate a circuit with LTspice. It is easier than you think. I will get you started in 5 steps. I will use this audio amplifier as an example. LTspice is free. You can download it at analog.com. We will start with the schematic. Then, we will download and import a simulation model. We'll create a new symbol with a symbol editor. Then we finish the schematic and simulate the circuit. Finally, we'll build and test the circuit on the bench. Now let's start with the schematic. Open LTspice and click on File, New Schematic to start a new schematic. Then click here to save it. Save as. Let's call it amplifier. Save. To add a new component, click here or press P. Let's first draw the input stage, the preamplifier. We start with the resistor. Press R and place it. If you click again, you will place another resistor. Press Escape to exit placement mode. Now right-click the resistor and add the value. This one is 10K. Press Enter or click OK. We will need 3 10K resistors. Go to Edit, Duplicate or press Ctrl C. Click on the resistor to duplicate it and place it. Click again to duplicate another one. Now press Escape to exit duplicate mode. To place a resistor, you can also directly click here or press R. Place the resistor, press Escape to exit duplicate mode, right-click and re-enter the resistance, 1K. Press Enter. Now we add a 5V power supply and the signal source for a sine wave. Click here or press V to place a voltage source. Place another one and press Escape to exit placement mode. Right-click on the voltage source, and for this one we enter the DC voltage, 5V. OK. Now we right-click on the second voltage source and we click on Advanced. Here we select Sine. The DC offset is 0, amplitude 100 millivolt, frequency 1 kHz, and we click OK. Now the star of the show, the LM358 op-amp. Click here or press P to place the component. Now let's look for an op-amp. Here I see op-amps. Double click. Let's make this a little bigger. LM108, LM308. Oh, there's no LM358. Now what? Let's close this and find an op-amp model online. When you search for SPICE models, you will often end up at Texas Instruments. Here I found the LM358. Then we scroll down. We go to Design and Development, Design Tools and Simulation, and here we see the SPICE model for the LM358. We download it, unzip the downloaded file. We only need the file with the .lib extension. Copy that, then we go to the folder where we saved our schematic and paste it. LTspice models for ICs are mostly .lib or .sub. For discrete parts like diodes and transistors, the extension is .mod. Actually, LTspice does not care about the extension. You can even call it .text. So we copied the lib file in our project directory. You can put it anywhere, but this way all information is in one folder, so we can zip it and share it with other LTspice users. Now we open LTspice and we drag this lib file into LTspice. Now this is the simulation model. It looks complicated, but no worries. LTspice will take care of reading it. Now if we look down here, we see subcircuit LMX58 LM2904, and behind it the pins in plus, in minus, VCC, VEE and out. This is the only thing you need to find. Now right-click on this part name. You see a menu pops up and we select Create Symbol. Now click Save. This will save the symbol or ASI file in the same folder as your schematic. Here you see the file and you see that LTspice has now made a symbol based on the simulation model. This way all the pins are assigned automatically. Let's maximize this window and let's tile the windows by clicking here. So this is the symbol, the model and the schematic we were making. Here you see the pins and you see the same pins in the symbol. Now I do not like the look of this symbol, so let's improve that. Let's maximize the symbol editor and first make a nice symbol shape. Press Delete or Backspace and delete the yellow box and press Escape to exit delete mode. Now we will draw a triangle. Go to Draw, Line or press L. Click to start a line and click again to end a line. And one more. And press Escape to exit line drawing mode. Now go to Edit, Move or press M. Let's move the VCC pin. Place it here and the VEE over here. The output here. In plus a little higher and in minus a little lower. Escape to exit move mode. I pressed L to draw some nice power lines. Now let's do something about these pin names. They link the symbol to the model, so we cannot change them. But we can hide them. Right click on the in plus pin and click here on None, not visible. Click OK. Then we make our own label. We go to Draw, Text or press a T and we put a plus here. We do the same for all the other labels. Put the minus here, plus next to the VCC and the minus over here. Now finally click on the name. Let's keep it, but let's make the font smaller. 1.0, press M to move it and put it here. Now we save the symbol. Click here or press Ctrl S. The symbol is finished. By creating the symbol directly from the model subcircuit file, LTspice automatically handles the file linking for you. So you do not need to type an include directive manually as you may see in other tutorials. Now we go back to the schematic and place our new component. Click here or press P. And over here we select our schematic directory. Click on refresh. And here we see our new symbol. Click it and select place. Now let's finish the schematic and add the output stage. We'll use a classic push-pull output stage which boosts the current to drive the speaker. Zoom out with the mouse wheel and click to drag the schematic. To move a component, press N. To rotate, press Ctrl R. To place a ground symbol, click here or press G. To draw a wire, click here or press W. You can go through the components with the wires. LTspice will not make a short. To move several components, click M and select them. copy with Ctrl+C. I forgot the decoupling capacitor here. Press delete, delete the wire. Place a capacitor, Ctrl+R to rotate it. Draw a wire, right click, and the capacitance is 10 microfarad. Now we place a diode. And to select the diode, right click, pick new diode. We select the 4148. Copy this diode. Then we need two transistors. One NPN, click here. Place it, escape. And one PNP. Now to select the transistor, right click, pick new transistor. And we want a PC337. And here it's complement, pick a new transistor, a BC327. Now we need some bias resistors. This one is at 1 ohm. And some bias resistors for the diodes. And now let's connect everything. To stretch a part or a part of the circuit, press S and select the parts you want to stretch. Like this, you can move them around and the wires stay connected. Now we still need an output capacitor and a speaker. So we copy this capacitor. For the output we want to have 470 microfarad. And our speaker is a resistor of 8 ohms. To change the name of a component, you can right click here on the name and we call it speaker. Oh, I see that this transistor is placed upside down. Let's move it. Press M to move, Ctrl+E to flip it, and Ctrl+R to rotate it until it's in the right way. Let's add some labels to make it easier to identify the signals. Click here to add a label or press N. First one is V in. The input, you make another label here. Let's rename that to V in C2. And one more label here, V pre amplifier. And finally, V out. Now we are ready to try the simulation. Click here or press A. We select Transient Analysis and we have a signal of 1 kHz, so let's go for 5 milliseconds for the stop time. Press OK and place the text in the schematic. Now click here or press Alt-R to run the simulation. That takes a long time. That did not work. What is wrong? Well, LTspice tries to calculate the steady state to start and cannot find it. Now this is very common in simulation. Let's make the steady state ourselves. Close this. Click here to edit the simulation. We set the stop time at 300 milliseconds and select here Start external DC supplies at 0 volts. Now the circuit will start from scratch. Press OK and we run the simulation. Now it runs. Let's have a look at the signals. Go to the schematic and as soon as you're close to a wire, you see a probe. Let's click on the input signal and click on the signal next to the capacitor. Here you see that the capacitor needs to slowly charge to its DC level. So here we reach the steady state. Let's look at the output of the op-amp and the current through the speaker. We can zoom in by dragging a rectangle with the left mouse. But there's a better way. Let's say we only want to see the last 3 milliseconds here. Click on the schematic open the simulation file and say we start to save data at 297 milliseconds. Now the simulation will only save the last part of the data. Let's run the simulation again. We now see the last 3 milliseconds, much better. To remove a waveform, right-click and select Delete this trace. Let's also remove the speaker current. And to zoom to all, you can click here or press space. If you left-click, you get a cursor. And you can measure the voltage on the crossing. If you left-click one more time, you get a second cursor. And you can check the difference between the 2 points. We know the input voltage is 100 millivolt peak, so 200 millivolt peak peak. This means that the amplification is 10 times. That is correct. So far so good. Now let's push the amplifier to the limit. So let's do 400 millivolt peak to peak. Right-click on the signal source and enter 200 millivolts. Let's simulate again. Oh, that does not look good. At the top, the signal clips at 3.6 volts and at the bottom around 1 volt. Let's have a look at the specification of the LM358. If we look at the voltage output swing, the LM358 cannot get closer than 1.4 volts from the positive rail and not closer than 0.75 to 1 volt to the negative rail. So if we use a 5 volt power supply, then there's not much left. So we need a better op-amp. Let's go back to the TI website. Here I found a better op-amp, the LMV358A, which is a rail-to-rail type. Design and development. Here's the LTspice model. Let's download it. Unzip. And again, we need the library file. Copy this one and paste it into our project folder. Now we go back to LTspice and open the library file. Here's the model. And the pins are the same, so we can use the symbol again. We select the symbol, we make a copy and rename it to LMV358A. Now we open it in LTspice. Now we go to Edit, Attributes, or press Ctrl A. The value must be LMV358A. That is the name next to subcircuit in the model. And the model file must be LMV358A.lib, the same as the model file here. Now save it. We go back to the schematic. We delete the old op-amp and replace the new op-amp. Maybe you need to press refresh here. Let's place it. Save the schematic. Now let's run the simulation again. Ah, much better. Now the preamplifier has a clean sine wave. It doesn't clip anymore. Let's add the output signal of the speaker. First we see that the waveform has no DC offset. That's because of capacitor C2. We also see that it's a bit clipped. Let's check the peak-to-peak voltage. Click on the trace label to add a cursor. And click again to add a second cursor. .66 volt peak peak. Now let's compare it with the pre-amplifier signal from the op-amp. That's about 4 volts. So we lose 1.34 volt in the output stage. That is 2 times 670 millivolt. Most of that is because of the base emitter voltages of the transistors and the bit in R5, R6 and C2. So, now the amplifier circuit works well in the simulator. Let's build the circuit and see how it works in real life. Here you see the input and output signals of the amplifier with the LM358. The yellow trace is the input signal. I use an offline HTML signal generator, which you can download from my GitHub page. The green trace is the output signal into an 8 ohm resistor. At 200 mV peak at the input, we have about 1.5 volt on the output. Now let's increase the input signal. The LM358 already starts to clip at about 1.7 volt peak. Now let's see if the LM358 does any better. I replaced the op-amp. Now let's increase the input signal. The output can go to 2.6 volt peak. Much better. Good. Enough signals. Now let's try some music. So with LTspice, you can test and troubleshoot your designs before building it. It's one of the most widely used simulation tools in the industry, which means there are endless online resources and a huge community to support you. If you like this video, please like and subscribe for more electronics guides. And I will see you in the next video.